We looked at some data for which we created a bar chart. We saw the data was normally distributed, but there are some outliers. We created a directed graphical model in order to incorporate prior knowledge on our latent parameters mu and tau. We found a true posterior as well as a surrogate posterior. Now we want to implement both of them and compare their performance. Hi, welcome to this video. Today we will implement the true posterior and the surrogate posterior for the normal distribution. So assume you have some data and you want to encode prior knowledge in order to regularize your estimate, and you also want to find full posterior distributions over these two parameters. And in the derivation on the true posterior, which we have done in an earlier video, we figured out that the true posterior is a Gauss-Gamma distribution for which we derived the parameter, and we then also derived the mode of it, which turns out to be the maximum a posteriori estimate. Then we did a similar thing for the surrogate posterior, where we applied the mean field approach in order to derive the posterior to be a product of a normal and a gamma distribution. Recall, this is not a normal gamma, it's just a product of these two. We derived the parameters for it, and we also derived a surrogate map estimate. And I will bring these two derivations over once we start implementing stuff. Let us first start with importing all the relevant packages. And I will first import a package in order to suppress TensorFlow warnings. Then we need TensorFlow itself, and we need TensorFlow probability as TFP. Even though we import TensorFlow probability, we will implement most of the algorithm in NumPy. So we also need NumPy, and later on we want to plot some contour charts, and for this we will use matplotlib in the pyplot interface as PLT. Then let us implement a main function, and first I will pass in here and I will create the switch in order to execute this file only when it is run with the Python interpreter, so that it then executes the main function. Let's start with defining constant and parameter. So defining constants and parameters. And since we want to work on artificial data, we have some true mu and some true tau or true sigma, whatever you want to call it. So we bring this down, and I will work with some data that is centered around 0.0, and it has a precision tau, or a true value of it, of 1.0. And this of course means it has a variance of 1,2 and a standard deviation of 1,2 in this particular case. Then we want to work on a data set with 100 samples. And I will select a random seed of 42, and we will use this for reproducibility. Then we also have our hyperparameters, and I will choose mild hyperparameters here. It is mostly about the algorithm. Of course, if you have a real-world data set, then you should encode your prior knowledge with these here. And they are an alpha 0, which I choose to be 1, a beta 0, which I also choose to be 1, a mu 0, which I choose to be 0. So I kind of define my prior knowledge exactly on the true value that I also use for creating a data set. Of course, in real life, your knowledge might not be as precise as this. And I will also define a tau 0 that is a 1.0. Then let's generate some data. Also, let me remove the additional spaces here. And for this, we first have to create a true distribution over x. I will call this an x true. And for this, we will use a normal distribution. And this normal is centered at mu true, and it has a scale. Well, we have to use the standard deviation. So we have tau defined. So we do 1.0 divided by tf dot square root of tau true. And that's our x true. And then we can create a data set for which we sample x true according to the number of samples. And here I will also fix the seed to the random seed in order that it always produces the same samples. And then I will transfer this array into the NumPy world in order for us to later perform our derivations on it. Then let's take a look at this data set at first, if everything is working so far. Save the file and then open up the terminal. Then we can execute our file, then it runs. It's the startup time for TensorFlow, And here we go. Here we see we have a data set that is mostly centered around 0 and with a standard deviation precision of 1. Then let's close this down. We can remove this print statement. And then we can start finding the two set of parameters. I will first start with the surrogate parameters. And for this, I will create a function that is called surrogate posterior parameters. And it takes the following arguments. It takes first an alpha 0, then a beta 0, then a mu 0, and a tau 0. So the hyperparameters, and of course, very first it has to use a dataset. And then lastly, since we have an iterative algorithm in here, I won't do any convergence analysis. I will just run it for a fixed number of iterations. For our particular problem, that's sufficient. You might have to adapt this if you are working with a more complicated scenario. And then I will also put a pass in here at first, because then we can create the interface in our main routine. And the output of this function will be an alpha s, a beta s, a mu s, and a tau s. And these underscore s, they indicate the parameters of our surrogate posterior. So we then call surrogate posterior parameters. And then we feed in the data set that we just sampled, as well as the alpha 0, then the beta 0, the mu 0, and tau 0. And I won't change the maximum number of iterations here. Then let us also create a print statement in order to look at them. But first I will introduce some comments here in order to say what we're doing. We are finding the parameters of the surrogate posterior, and then let's print them. That are the parameters of the surrogate posterior. And recall, the surrogate posterior was not a Gauss-Gamma, it was a Gauss-Gamma. So these are two independent distributions. Then let's print the parameters. I will use a formatted string here. And we have first the alpha s, where I will use the alpha s that we just calculated, and I will use a 1.4 in the floating point precision. And then we have beta s, mu s, and we have tau s. With this down, we can then go back up and implement the VI algorithm. So essentially, this is the VI algorithm by mean field approach. And for this, I will bring over our findings that we have here. And recall, we have these parameters that we have to find. And we first created some abbreviations that simplified our computation and also increased their performance. So we will first get a mu MLE. For this, I will use the mean of the dataset. Then we have a variance MLE, which will be the mean of this augmented dataset. So dataset minus mu MLE in brackets raised to the power of 2. And then let's bring this down a little bit. And then we can start first with the mu s. So we have a mu s, which is given as tau 0 times mu 0 plus n. Well, okay, we don't know n yet, so let us first infer the n from the dataset. And n is dataset.shape. And then we have to use the first axis. I mean, it's just a one-dimensional array, so the one axis that it has is the number of the samples that we have drawn. And then we can go back here and do n times mu MLE. And lastly, we have to divide this by the tau 0 plus the n. Then let's go to the alpha s, so the alpha of our surrogate posterior, which will be alpha 0 plus n plus 1 divided by 2. Then we can go on and we have a tau s, and here we see we have this circular dependency, so we have to start our iteration, and I will start by guessing beta s, and I will guess beta s to be beta 0. So let me note this down, guess beta s to be beta 0, but you could also start with a random guess, and then you start your iteration. I will do my iteration over this max number of iterations, and then we can implement them. First, we have the tau s, which is tau 0 plus n times alpha s divided by beta s. Then also let me adjust the spacing here. And then we have the lengthy formula for beta s, which is beta 0 plus, and I will just use some lines in order to make this more visually appealing. Then we have 0.5 times tau 0 plus n, and then we divide this by tau s. And here we have our circular dependency. Then we have to add the next term, this one here, which is tau 0 times n times mu0 minus mu mle in brackets raised to the power of 2. And we divide this by 2 times tau 0 plus n. Then we add the last term, which is 1/2 times n times the maximum likelihood estimate of the variance. So we have 0.5 times n times variance MLE. And then we can return our values that we found. So we return them in the order alpha s, beta s, mu s, and tau s. And also the naming should be correct here. And hopefully, if I haven't made any mistakes in here, then we can run this script again and see what the parameters of the surrogate posterior are. And that seems, of course, interesting. I mean, we can't interpret them yet because we don't have any reference, but at least our script runs. So let's do the same thing for the parameters of our true posterior. So I will move this over here, and then we do the same thing for the true posterior. So I will also create a function that is called true posterior parameters. And it takes also the data set. It takes an alpha 0, it takes a beta 0, it takes a mu 0, and it takes a tau 0. And compared to the function on the VI algorithm, it does not take a maximum number of iterations because we found a closed form solution that doesn't even need an iteration here. So then I will also create a pass in here in order to first fix the interface on our main function. And I will mostly copy this down from here and then adjust what is different. So of course we call true posterior parameters here. And I will also use a different index. I will use the index capital N in order to denote that these are the parameters of our true posterior. Then we should also print them. And here we then have the true posterior. And the true posterior is indeed a Gauss-Gamma or normal gamma distribution. So it has the dependency between tau and mu. Then let's note this down too. So we have an alpha n and an alpha n here and the same game. It's a little tiring, but you get the point. So we have to change this and this here. And lastly, this one here. So then let's go back up and implement the true posterior. For this, let me bring over the derivations that we did, and here we have the corresponding parameters. Then let's start again. We first have to infer the number of samples again from the data set. So I will use the same strategy here. And then we can start with implementing them straightforwardly. And we have first an alpha n, which is alpha 0 plus n divided by 2. Then we have our beta n, which is beta 0 plus, and I will use the same strategy to go in the next line in order to make this cleaner. And we have 0.5 times tau 0 times n times mu 0 minus mu mle, well, in brackets squared. And we don't have this mu mle yet, so let's do the same thing that we did up here. I will just copy these two down, then we also have them here, then we have the mu mle, then we can divide by the tau 0 plus n. And if you got lost, I'm here right now. Then we have plus and go back to the next line. And then finally this term here, which is 0.5. And we had n times sigma squared mle, or the variance mle. So n times variance mle. And that is our beta n. Then let's go down to tau n and mu n. So here we have tau n, which was tau 0 plus n. And we have mu n, which is tau 0 plus mu 0. That should be multiplied. And then we have n times the mu mle, which is our x bar. And then we divide by tau 0 plus n. And then we have found our 4 parameters here. Then let's return them too. So we return them in the same order. So alpha n, beta n, mu n, and tau n. And let me put this back over here, and then we can run our script too. And then we should have also a print of the true posterior parameters. And let me go back down to this point here, and then let's compare them. And we see that the parameters of alpha s and alpha n is quite close. For the mu s, we actually have identical values. And for the taus, they are also not that far apart. But again, keep in mind, these are parameters of two different distributions. First, a Gauss times a gamma, and then a Gauss gamma. And now it is also interesting to compare the modes of these two distributions. So the map estimate in essential. And let us start with the surrogate map estimate. And I will bring over the derivations for the surrogate once again. And here we defined this according to this formula. So these are the modes of our two distributions, or our two independent distributions. So we have a mu map surrogate according to a mu s, and we have a tau map s according to, well, an alpha s minus 1 and then divide by beta s. Then let's print them. So these are surrogate map estimate, and we have a mu map s according to the mu map s that we found. Of course, it should be a formatted string index, and then we also do the same floating point precision here. And we have a tau map s according to tau map s that we found, and also use the same precision here. And we can make the same game for our true posterior map. So let me bring over the derivation for this one. We did the derivations by hand and found it according to this and this one here. So we have the true map estimate. So we have a mu map n. So n again for true, if you would call it like this. And here we have it is according to our mu n. So this is according to mu n, or in other terms, the mean of our true Gauss-Gamma posterior. And we have a tau map n, which is found by this formula here. So it is an alpha n minus 0.5 divided by a beta n. Then let's also print this. And we see, if we go down here and print them, then we have here the true map estimate. Also, let me change out the indices, and then we should get, and then we get again our parameters, and then we should also print the map estimates. And here we go. And as we see, we have a map estimate for the surrogate and the true map estimate that actually coincides. That's interesting. And for the tau map, we have something where our surrogate is actually better, maybe at least in this fourth digit after the comma, but overall they have kind of like a similar performance. This can be due to the data set, that the surrogate posterior is a little bit better. In general, if you observe this maybe with more data, then you might see that the true map is a little bit better. But of course, the most interesting aspect is to look at some contour plots here. For this, we have to create a mesh over which we evaluate the functional form of the surrogate posterior and the true posterior. So let us start with defining these two, because they are joint distributions, and we will use TensorFlow probability. So we will create generators for them, and I will define them all the way up here. So first we define the true posterior, which is a Gauss gamma, and it takes in the parameters alpha 0, beta 0, mu 0, and tau 0. Don't be confused. I use the index 0 here in order to differentiate them from the taus and the mu's that we will draw, or that these distributions are defined over. Then once we instantiate them, we will of course bind them with the parameters that we found with our derivations for the true posterior and the surrogate posterior. So the first random variable that is inside this distribution is the tau, and it is a random variable, so we have to yield it. Additionally, it is also a root node, and we will indicate it as a root node by joint distribution coroutine dot root, and then its functional form is a gamma, and the parameters of the gamma are given by alpha and beta. And so we plug in alpha 0 and beta 0, and I will also give it the name, which is tau. Then the second random variable in this directed graphical model, or in this posterior, is the mu, and In this case, it is not a root node, but it is a random variable, so we have to yield it. And its functional form is a normal distribution with the location according to mu0, and the scale is, well, it is tau 0 times tau, it is precision. So in order to get its scale or standard deviation, we do 1.0 divided by tf dot square root of tau times tau 0. And let me also indicate that this is the true posterior. And then we have to define our surrogate posterior, and this one was a Gauss times gamma, so it is Gauss times gamma. Interestingly, it takes the same parameters. It takes an alpha 0, a beta 0, a mu 0, and a tau 0, and as said, it is the surrogate posterior. And we also have tau and mu in here, so tau, and tau is again a random variable, and it is also a root node, so we have to indicate it by joint the distribution coroutine dot root, and then its functional form is a gamma distribution according to alpha 0 and beta 0, and its name is also tau, and maybe then we should also add the name here, which is mu, or without the colon, and then we have the mu, which is a random variable. And now the big difference to the Gauss-Gamma is that this one is also a root node, because it has no dependency on tau, because these two distributions are independent. So it is a TFP dot distributions dot joint distribution coroutine dot root, and then we have it as a normal distribution with the location according to mu 0, and its precision only according to tau 0. So the scale then becomes 1.0 divided by the square root of tau 0. And then we should also add a name here, and the name is mu. And I see there is a wrong bracketing here. This one should be here. And up here, this should be fine, I think. Aside from this one, which has the same error. We would have seen it then, but with this one, we are fine. And now that we have the distributions down, we can instantiate them correspondingly with the parameters that we found. So let us go back down here and let us first do it for the surrogate posterior. So we get that the surrogate posterior is a tfp.distributions.joint distribution coroutine auto-batched, and we have to call it with a function or generator that does not take any arguments. So we have to bind the arguments of our generator. So it is a Gauss times gamma, and it was taking the parameters alpha s, beta s, mu s, and tau s. However, if we are calling it with these parameters, then we run into trouble, because in NumPy computations are done with 64-bit wide floating point numbers, and by default TensorFlow is using 32-bit floating point numbers, so we have to convert the NumPy objects into TensorFlow objects, and we can do this conveniently by saying that alpha s, beta s, mu s, and tau s is tf.convert to tensor of a tuple of the alpha s, beta s, mu s, and tau s, and with this we are fine again. Then let's do the same thing for the true posterior. So I will just copy this down, and here we go back down here, and then let's change the indices of all the parameters in here. It's a little tiring, but I think you get the point. So this should also be here, and then we have the not the surrogate but the true posterior. And the true posterior is also a joint distribution coroutine auto-batch, but it's using a different generator. It's using the Gauss-Gamma Generator. And it is also not taking the parameters of the surrogate, it is taking the parameters of the true posterior. So let me note them down here, and then we're good to go. With this, we have our two distributions, and we can then query their log probabilities or probabilities in order to create our contour plots. But just as a reminder, we did the map estimate here, and this essentially is as if we would for the true posterior, we would call true posterior.mode or surrogate posterior.mode. But of course, this does not work because in general, TensorFlow probability can't calculate the mode for an arbitrarily complex joint distribution. Then let's go to the contour plots. For this, we first have to define ranges over mu and tau that we want to plot and then create a mesh. So I will start with a mu range, which is tf.linspace, and it is starting at -1 going to 1, and we want 40 samples. A tau range, which is a linspace, because tau has to be strictly positive, I will go from 0.01 to 1.5, and I also do 40 samples here. Then we can get a mu mesh and a tau mesh according to tf.meshGrid, plugging in these two values of mu range and tau range. And then we can concatenate them in order to create something that I might call points 2D. And here we have to take care in our two directed graphical models that we created up here. Tau is the first random variable, so it also has to appear first in this tuple. So we have tau mesh and mu mesh. Then let's query the log probabilities of the surrogate and the true posterior. So I will call this log_prob surrogate posterior, which is the surrogate posterior dot log probability on these points 2D, and it will associate each of the points in this two-dimensional mesh that is consisting of 40 times 40, so 1600 numbers. It will associate it with its corresponding log probability. Similarly, we can do it for the true posterior, which is true posterior dot log prob of points 2D. Then let's create our contour chart, and we will use Matplotlib for this. So I will first create a figure, and I will use this lazy functional interface. So then we have to use, okay, let me go down a little bit, plt.contour, and it's first taking the mu mesh, then the tau mesh, and then the log prob surrogate posterior, because we will first start with the surrogate posterior, and the number of levels, let's say we want 100 contour lines. Also, let us introduce some labels, and we will do the X label should be the mu, then the Y label will be the tau, and let's also add a title, which would be surrogate posterior, and then let's copy this, and in the end we should also add a plt.show, and I copied this in order to just change it to the true posterior. So we have to change this one here, and then also should change the title of this plot. There we go. And if everything worked fine, hopefully we should now get some plots. The problem was that our mesh wasn't in 32-bit wide floating point numbers, so I added a casting here from the 64-bit wide that is standard when using linspace to the floating point number with 30-bit wide. And then it runs. You also see the output here. I checked it before, then we can run it again. And two figures pop up. The first one is for the surrogate, let's make it like this, and the other one for the true posterior. And what you see here are contour lines of the log probability and the two main points. First, we can rediscover the map estimates here that we also calculated here. So we have a surrogate map estimate of around 0 and 1, so I think that makes sense. Here's the center. The same is for the true posterior. It's a little bit to the right, we see this, but this is probably because our data wasn't too perfect. But I think the most interesting aspect here is that due to the fact that our true posterior is a Gauss-Gamma distribution, we get those non-axis aligned contours. And by axis aligned mean that here we have ellipsoids, whereas here we have these classical Gauss-Gamma triangles that are a little bit inclined inwards to the maximum of this distribution. And I think this also portrays the big simplification for the surrogate posterior, where we say that the tau and the mu are independent, or the distributions over them, whereas in the true posterior they are dependent. But one really important remark, here it did not greatly matter. So in other terms, we were able to recover a map estimate that is almost the same of the true posterior, in our very case a little bit better also, and that's sufficient. I mean, if we are able to use the surrogate posterior in application scenarios where we can't even find a true posterior, or maybe also in points where the surrogate posterior is just easier to compute, and we get an approximately perfect true posterior, then we should use it, right? That is absolutely fine, and that motivates the usage of surrogate posteriors. Even though we have more features in the true posterior, those features might not be as relevant to us as the overall shape of the distribution, which is definitely captured by the surrogate posterior. And I encourage you to play around with this script, change a little bit of the parameters, and see how this affects the contour lines, the map estimates, etc. Then I hope you enjoyed this video. If you did, then please consider liking and subscribing. I would extremely appreciate this. Here you can now see similar videos, and then I hope to see you next time.